So we're doing orbital notation. Whoop, N-O-T-A-T-I-O-N. All right. And we're looking at the periodic table. And hydrogen and helium are both in the first primary energy level. And helium actually belongs here when we're talking about orbital notation and electron configurations because it's in the S sublevel region over here, these first two columns. So for the first two electrons in orbital notation, in the first primary level, you only have an S sublevel, and those are the two electrons for hydrogen and helium. All right, so we're trying to get right now, we're going to go to, let's say, magnesium for right now, okay? So I'll put the symbol for magnesium out here in a colon. That is required. I need to know what element it is. If you don't have the symbol out there, I don't know if you did magnesium or manganese or something else. So you need to make sure you tell me what element you're writing the orbital notation for with a colon, okay? Then, after you fill up the first primary level, we're going to the second primary level. That's 2. We start with this S sublevel region over here. So those are S electrons, and we have 2 electrons represented by the position of lithium and beryllium, and the orbital is represented in orbital notation as a box. Arrows represent the electrons, one up, one down, to represent their opposite spins to show their quantum entanglement. Okay? And then we're going to go over here to the P sublevel region, and that's the second row still, second period, and the position represents then the second primary energy level in the electron cloud, P sublevel region within that electron cloud, and 3 orbitals over here. So 3 boxes, 1, 2, 3. And since we're going down here to magnesium, we need to fill up all of these. That's 1, 2, 3, 4, 5, 6 electrons. 1, 2, 3, 1 in each box, and go back and pair them up. School bus rule. Okay? And when we get to magnesium, we need 2 more electrons, but now we're in the third row of the periodic table, and that position represents the third primary energy level of electrons in the electron cloud. Those electrons are in an S sublevel region, and one orbital in an S sublevel region. Magnesium is going to have 2 more electrons, 1, 2.
So everything under that is going to have all of that plus more?
Yes, everything under that is going to have all that plus 1, plus more, however many more you need, because you keep building, basically. That's the way you think about it.
Yeah.
Okay? All right? What now? I'm going to show. Well, I'm going to show you a way to do that. I showed you once, but I'm going to show you again before the day's out on how to do that. Okay. Well, just bear with me. We'll get there. Okay, we'll keep practicing. Got a lot more to do. Okay? All right. So you can work with a neighbor who gets it. Okay? On this next one, I'm going to let you guys do sulfur. I'm going to let the whole class do sulfur. So I want you to write the orbital notation then for sulfur.
What is abbreviation for that?
This is what I do. Can you explain again the good boxes? Like I got down how to do it, but I still don't really understand why there's 3 boxes.
You don't understand why there are 3 boxes?
Like I know where to put the arrows at.
Okay. You can only put 2 electrons in an orbital. The boxes represent orbitals. Okay? If I have 1, 2, 3, 4, 5, 6 elements over here in this 3p sublevel, okay, then I need 3 orbitals.
Okay.
Once I put any electrons in 3p, the orbitals are there even if electrons aren't there. It's like I have 3 houses on the block, only 1 person living there. The houses haven't gone away, okay? And so with sulfur, I need 4 more electrons, 1 in each box, and then we pair up 1 to get this sulfur. Yep. S sublevels have only 1 orbital. And it has to do with 3-dimensional geometry and force attraction and various things like that, quantum mechanics, wave theory. We don't need to get into that too deeply at this point in time. Unless if you want to, go do the research or come in and see me and I'll try to help you, but it's really not necessary to know that to know how to do this. It's way beyond the scope of the class. Yep. S's always have 1 box, P's have 3, D's have 5, F's have 7. 1, 3, 5, 7. Yeah, Taylor?
So, 1s, does 1s like, by itself with the two boxes, does that represent hydrogen or hydrogen and has like two electrons?
Okay, 1s holds electrons in the sublevel S, in the primary level, energy level 1, for any elements. But if all we have are electrons in 1s, then that would only be the element hydrogen or helium. You'd have 2 electrons for hydrogen, 2 for helium. Now, I want to say this without, just bear with me because we'll learn about this more later, but we also have some ions that have only electrons in 1s. Don't worry about that right now. We'll get to that. Okay? All right, so far? Okay. It's just, hey, right now we just learn how to put them in there. Okay? And we'll learn to use that when we're doing bonding later. Okay? That's the point right now, is learn to use it, learn to build it, to see how bonding is done later. But why? That goes way beyond the scope of the class. Even though science is all about why, I agree. Let's try to stick with just how do we get it done right now. Okay? Fair enough? All right. Does everybody understand how we put electrons into this sublevel? Down here, 4p. How to build that? Huh? I'm sorry, this is 3p, right? 3p. Okay? All right. Let's everybody do calcium now, because it's going to work the same way up to calcium. Then we're going to have to change some things. We go to calcium and do an orbital notation for calcium, okay?
Okay. But it's the same thing.
All right. Guest teacher. Have at it.
Yo. Okay. Alright, so you have one little box here, and it's going to be a 1s, and a up arrow, down arrow. Then you have another little box, and it's 2s, up arrow, down arrow. Now we got 3 boxes, and it's a 2p, up arrow, down arrow, up, down, up, and down.
So while she's doing that, your job is to watch what she does, and if she makes a mistake,
3s
help her out.
always has 1 box. Go down. And
So
then
far, so good? Okay.
the P's always have 3 boxes. 3 P, up, down, up, down, up, down. You want me to just keep going across? And then the S's always have 1 box, and it's gonna be up and down. See?
Looks good to me.
Balls?
Nicely done. Hey, you write neater than me. That's great.
I have a question.
Yep.
How do you know, like, the 3p, how do you know when you have to go back and, like, put it down and, like, match it up? I don't know.
All right. The first 3 arrows are always going to be up in a different box. And then you go back and fill them up before you go to a new sublevel.
So they have to be paired up before you move on to it.
Yeah, they have to pair them up before you move on to a new sublevel.
Okay.
Okay? Doing okay? Alrighty. Now that we're doing okay, let's see if we can mess you up a little bit. Scandium. Okay. So let's pay attention here. Scandium, you notice how we've kind of got an empty space right in here? Okay. In one sense, this whole section right here from scandium to zinc kind of belongs right here. But in terms of the proton numbers or the atomic numbers, it belongs here. And the reason it kind of belongs there is because we're actually putting electrons, when we get to scandium and titanium and vanadium, we're actually putting electrons in the 3rd primary level, not the 4th. So let me show you how that works. We're going to write all of these same orbitals and electrons for calcium. This time it'll be 5 boxes because there are 10 elements there, or actually there are 10 elements there because there are 5 orbitals. But we often think about it sort of backwards when we're doing this. All right, so the electron that we're going to add, the one more electron we're going to add, the one extra electron we're going to add for scandium, is not going to be placed in the 4th primary level. It's going to be placed in the 3rd primary level, and this whole section here is the D sublevel. So it's 3D, and as several of you have already noted, since there are 10 elements in here, that means we're going to be adding, at least in this section, we're going to be adding 10 electrons, and we need 5 orbitals for that. So we're going to need 5 boxes for 3D, or all the D sublevel regions. These sublevels, we're going to have 5 boxes. Okay, we just need 1 electron in there. Exactly. The orbitals are there even if we don't have electrons there. Okay? And, well, I don't want to get too deep into that. Yep.
So you said the Banfield to zinc row is actually supposed to be a level higher, which is why we put the...
Well, a level higher on the periodic table, a level lower in terms of numbers and closest to the nucleus, yes.
Is that for all D ones?
All the D ones drop back 1. And the F's drop back 2. We'll get to that. Okay? All right. Y'all kind of got the idea? All right, then write orbital notations, or write the orbital notation, please, for copper. Write the orbital notation, please, for copper. All right. So, there is an exception for copper. We're not going to learn it in here. We're just going to assume that this is the correct way to do it. When we go to the this P sublevel region, we're going to put electrons back in the same primary level we started with at the beginning of that row. That we began over here with 4s. So these electrons are 4p. You got that? Any questions? Then why don't we all try arsenic? Everybody do arsenic. All right, so here's the orbital notation for arsenic. We finished up filling up 3D. We have 2 electrons in each of those 5 orbitals. So the remaining 3 electrons for arsenic are put in the 4th primary level. That's the level we started with right here. We drop back 1 for 3D. We go back to 4. We couldn't stay in 3D because we've already got 3P, because we already have a 3P, okay, down here. So you can't do 3P twice. There's only one 3P. So the 4P has 3 electrons in there, 1 in each box. And the rule is you always put 1 electron in each of the boxes, and then if necessary, go back and pair them up. Everybody got it?
This is 14 or with all of them? What is like the electrons? Like why didn't you put 2 in one box or whatever?
Because I only needed 3 more electrons here. Once I had 3D filled up, I only needed 3 more electrons. Is that the question you were asking?
No, I thought you would put 1 up and then 1 down and then 1 up.
No, it's 1 in each box, and then if necessary, pair them up. After you have 1 in each box, then you can pair it up.
All of them.
Yeah, in every section.
Okay.
So even in the D sublevel regions, okay, you're going to put 1 in each box, and then go back if necessary and pair them up. Yeah. You got. Yeah, good. That's the best kind of answer.
Why didn't you pair up the first one then?
Which first one?
Or the why didn't you?
Was he able to answer your question sufficiently?
Yeah.
Okay. Now, is that water you're drinking?
Oh yeah, we can't drink it.
You can't drink in here. The only exception is I'll let you have water if you keep it in your book bag.
It is water, but
Yeah. That's fine. If it's water, then you can drink it and put it back. You're good. Okay? All right. I just don't see many people bring a cup like that for water.
it's water.
Take your word for it. But of course, I can always go over there and, make sure.
I just got a new cup.
All right. Okay, so the next row, 5, works exactly the same way. Okay? We're only going to have that D sublevel that's going to drop back. So 5s, then 4d, then 5p. All right, you want to practice one of those? Somebody said no and somebody said yes. Huh? Huh? You want? Yeah, you want to pick one? Okay, which one do you want to do? Make it iodine. Make it iodine. Make it out. What do you want? Any. I guess anywhere in 5s is fine with me. I mean, the fifth row anyway is fine. What? Ruthenium. Okay, let's do ruthenium, guys. Ruthenium is the assignment. Are you ready to do this? All right. What? I mean, for one of these right here? Yeah, it's got to be lowercase letters. Okay? Got to have lowercase letters. No capital letters for these. Those capital letters are reserved for other things. Okay? All right? So there's 6 electrons in the 4d sublevel for ruthenium. Here's ruthenium right here. 1, 2, 3, 4, 5, 6. The placement of these elements tells us that there are 6 electrons in this sublevel right here. Okay? And so we put 1 in each of these boxes and go back and pair one up because that's needed. That makes sense? And then after we get into past ruthenium and get over here into the p sublevel region, that's going to be back into 5p sublevel over here. Okay? So these electrons are 5p. Got it? All right then. We're going to go to the next row. And we're all going to do, well, I'll tell you what. We're going to be doing cerium, but I want you to stop with the last electron for lanthanum, and I'll show you where we go from there, okay? So go ahead and start writing the orbital notation for cerium, but don't put in that last electron. Does that make sense? Huh? Yeah, 58.
Can I go to the bathroom?
I hope you can.
May I go to the bathroom?
You certainly may. Okay. All right, so this is where I ask you to stop for cerium. The idea is that if you look on the periodic table where cerium is, it's not in the section we call 5D. It's in the F sublevel region. And F sublevels drop back 2 levels from the primary level, from the period level, okay? So it drops back 1 from 5 and 2 from 6. So when we get to F, it's 4F, okay? So we're going to put 4F, and how many of the boxes do we need now? These 7 boxes, but 1 more electron, correct. 1, 2, 3, 4, 5, 6, 7. So cerium just has 1 electron in 4F. Whoop, I'm off the screen here. Okay. 7 boxes, 1 more electron for cerium. Huh?
Is there not like a shorthand way at all?
Shorthand is not really something that you do for orbital notation. We will for the cubes. Okay?
Will 5D always be empty after the fission?
What now?
So will 5D always... Oh wait, never mind.
Fill up F before D.
Never
You
mind.
fill up F before D. And once F is full, you go back and start filling up D. Okay? So to practice that, let's all do hafnium. Hafnium.
Wouldn't the shorthand be like 6S5D?
Yep, it would be if we had one.
We cut down everything else.
Right. So let's do hafnium, please.
What is happening?
HF, number 72, hafnium.
Clarify.
Okay? All right. So hafnium only has 1 more electron in 5D than cerium. I'm sorry. Yeah, than cerium. Okay, so cerium just had the 1 electron in 5D represented by the position of lanthanum here. And then we have to fill up this whole section of 4F before we come back and put that 1 electron in right here for hafnium. Does that make sense? So it's just a matter of following the numbers in the periodic table and putting the electrons in the appropriate section. That make sense? Yes? No? Maybe? All right. Anybody struggling right now to understand what we're doing? All right. Now, I'm going to jump to something for your element cube project, because if some of you have these really large elements like this, try to put all that in that bottom box, yeah, it's not going to fit. So just for the element cube, it's not allowed anywhere else, any other time. Okay? Not on tests, not on quizzes, not on homework. But just for the element cube, I'm going to let you do a kind of shorthand, okay, for elements that are large like this. Okay?
What's the cutoff?
The next lowest noble gas. Okay, here's hafnium. Hafnium is, I know what you meant. But we're going to go back, count our way back until we come to a noble gas. Okay? As long as there is a noble gas below the element you're working with. Let's see. How about we do after you get past neon? Okay? All elements past neon. Got it? Then I don't want you to go back to helium. That's just too little. But after you get past neon, you can use this shorthand, but only for the element cube, not on test quizzes or homework. Got it? All right. So, what's the next lowest noble gas for hafnium? Xenon. And if you write the orbital notation for xenon, you'd stop right here with 5p. This is the orbital notation for xenon right here. And what we're going to do for the element cube only is we're going to replace all of that with a symbol for xenon. But that's only for the element cube project. Not any other time. So for the element cube,
What if it is a noble gas?
you have to go to the next lowest noble gas regardless. Okay? So if you're doing xenon, you'd have to start with krypton. Does that make sense to everybody? Okay? If you're required to do the orbital notation for xenon, then you have to put in krypton to replace everything below that, and then finish with xenon. Let me show you how to do. Let me finish this one as the example. Okay? The element cube only. Okay, shh, pay attention. Here's the symbol for hafnium, and we're going to replace all of this with this symbol. Okay, and then we can finish it out.
See, that's what's on the Wikipedia page. It has that. I was wondering what that was.
Are we allowed to do that for electron configuration too?
Yeah, electron configurations is actually allowed all the time, but it's not allowed for orbital notation except for the element cube. Okay, so that would be an acceptable way to write the orbital notation for hafnium on your element cube. Okay.
Do we have to rewrite it, right?
No, actually, you don't have to write it. Now, let me show you how to do that.
You have it on the page, yeah.
Okay, so here's one I did it already. So, tell you what, let me go back here, take this out, and I'll show you how I did all this.
Is it due tomorrow?
That's the idea. So look, you type in hafnium, you put in the colon, you put in the brackets with xenon in the middle, and you go in here and copy and paste what you need. So if I need 2 arrows, I'm going to copy that, and I'm going to paste it right there. And I can change 1s to 6s. Okay? hit a couple spaces, and I need 5D. Well, my first two orbitals for 5D have only one arrow. So I copy that one, put it in twice, and then I need a bunch of blank ones. I need 3 blank ones, right? 1, 2, 3. I can take out these numbers and letters here at the bottom. And change that to 5D.
So what if it doesn't take up like the whole
What do you mean doesn't what if it doesn't take up the whole cube?
and then we just leave it like blank?
You could, I suppose. Okay. And then for 4F, I need a whole bunch of these with 2 arrows. I need 7 of them. 1, 2, 3, 4, 5, 6, 7. Only want to change the first one to 4F. And I can take these out. Okay. And there's your orbital notation for hafnium. Got that? All right, I'm going to leave that there for a minute. Now we're going to talk about electron configurations. So those of you, if you know how to do electron configurations, raise your hand. Some of you know. Couple of you? Okay. So you see who raised their hand back here? They're the go-to guys to help you. All right? Electron configurations. Now once you do orbital notation, electron configurations are really easy. Okay? Let's go back here and look at arsenic I was doing a moment ago. I started ruthenium here and said, wait a minute, I want to turn my paper sideways. That's why I've got this marked out. Okay? Alright, so for arsenic, for electron configurations, it's kind of a shorter version of this. It has the benefit of being shorter, but you have to know more to use it. Okay? And you can't use it to explain some things you can explain using orbital notation. That's why you need to know both in high school chemistry, okay? But here's how you do electron configurations. You write the symbol again for arsenic and a colon. And instead of writing 1S and the box and the arrows, you write 1S and count the arrows, and that becomes a superscript. So it says 1S2 because there are 2 electrons in that S sublevel. And for 2S, it's 2S superscript 2. For 2P, it's 2P6. And just keep going. Okay? 3S, what is it supposed to be? 2. 3P6. 4S. 2. Then 3D. 10. And 4P. 1, 2, 3 electrons. 3. Okay? And that's the full electron configuration for arsenic. Now, while the shorthand version of orbital notation is only allowed on our element cube, the shorthand version is allowed, if I say it's allowed, okay, almost any time for electron configurations. So what I want to do then is replace the all of this that is part of a next lowest noble gas with that symbol. So let's see, let's find arsenic here. Here's arsenic. That's number 33. And if I count backwards, I'll eventually come to argon. That's the next lowest noble gas. And argon stops at 3p6. So all of this right here is the orbital notation for argon. So we can write a shorthand version that says arsenic, brackets, argon, and then 4s2, 3d10, 4p3. Does that make sense? Now I expect you to be able to do both the long version and the shorthand version. Okay? Got that? In fact, for practice, let's all do orbital notation electron configuration, and let's call it noble gas electron configuration for seaborgium. Seaborgium is named for the scientist who led the team that probably created more man-made elements than any other group of scientists.
What was that first one after the word do?
Do orbital notation, electron configuration, and noble gas electron configuration for seaborgium. That's the homework in addition to finishing your cube.
Where is it?
What is that?
Oh, SG?
Mm-hmm. You got a periodic table with all that on there.
Yeah, I like that. Yeah, it does say that.
But you do have a periodic table that does.
Just the last
What is it, SG?
But
It's on the very bottom.
but by giving it to you this way, I'm helping you to start familiarizing yourself with those symbols, okay? This is homework. Not now work, it's homework, okay? What? Oh, sorry. There you go.